First, I would like to have some disclaimer. First time I presented this subject, similar subject, not quite the same, but this year in Paris on the LFCon conference, when this new machine we start production, and not only machine, but also this is about a subsystem, propulsion system, drives, and machine asset together. This time, looking on this conference and subject introduced here for last 2 days, we are on a very high level. Green, lead, and huge system, how to save energy, how to do better job. I want to bring you a little closer to know how it's done on a component level or small subsystem levels, and how difficult job it is to achieve high efficiency, small footprint, reduction of mass, reduction of cost, and to make a much more useful and easier for construction. Let me start with trends in hoisting machine for very, very tall buildings and high almost mega buildings, what we have talking during this conference. What is needed? It's needed increase capability to lifting. Because what was said here, masses, when you're going higher, masses of ropes, I understand that this ultra synthetic ropes is a future, but so far it's very experimental. We probably for next 5-10 years, we will still have a much more percentage of steel ropes. And I hope that we will come to this point, but let's say we have to address this issue now. Second, reduction of weight and size of the machine. Why weight? I will give you only an example in a second, in the next slide. When machine is built and have to take off from the ground to the level of machine room, this machine can weigh 20 tons. And with structure of buildings, what we have right now, when it's a core, and you cannot place any lifting devices like a crane on a corner of the building, you have to make a special crane or platform to reach for this machine and pick it up and go 700, 600, 500 meters up. And this is very, very challengeable job and very, very costly. We did this in Burj Khalifa, and we know what it means, and how logistically difficult it is, and how costly it is. This is why when you reduce a mass, you can easily take it, or do modular design for the machine and do it in few parts, and assembly on a spot in a machine room. And here is also an example why size matter. Otis have, for about 20 years, using Skyway machines, which is predecessor of the SkyMotion, what we're introducing this year. And you can see envelope for these machines, and now how the smaller is equivalent to these machines. It's required to sometimes to place them in a vertical direction, one over another, to fit over the elevator shaft. This you can see on this first picture. Second, showing how this now can be done with space around and fit to latest code requirements. Maybe I would say, as David said yesterday, not requirements, but guidance. What this code guiding us, how to do it, what kind of utilize sizes of machine room and elevator shifts should look like. Third one, simplified installation. This is why I said when you're taking off and putting a few up with few components and put them together as a one machine. Also low maintenance, what it means. Relubrication, inspection, checking if this is working. And this should be addressed also by new design, and this was also some challenge to us. Environmentally friendly design means, that, again, usage much less chemicals like lubricants, and really recycle it. Now the machines. What are the SkyMotion machines? About the drives I will talk a little later. We have three types of SkyMotion machines which are addressing all needs. And this is like the biggest machine right now, the most capable machine on the world so far. And I don't know if we need more if you have the ultra-right robes. Yesterday was a question here during the session, last session, what about the size of machine? Size machine is defined by power. Power means that this is multiplication of speed, capability of weight to pick up, meaning torque. And weight means weight, like ropes, counterweight, car mass, and also the load, how many passengers we can leave. And you can see that these three machines are divided in three. The biggest one is SkyMotion 800. 800 means that maximum torque, acceleration torque can be about 80 kilonewton meters. 400 means 40 kilonewton meters. And 20 and 25, this smallest machine is divided in two. Simply 250 is to fill the gap between these two from economical reason and to be better to needs of the system. And you can see that we can do with the 400 machine up to 20 meters per second single deck, and up to 5,000 duty load with 50 meters per second with double deck. It's not here, but also we can do with biggest machine even triple deck. We are capable, Otis is capable to do triple deck. It will be required, of course, for building will be justification for that. And this is basic parameters, but what I want to point out, how these machines are smaller comparing to predecessor of these machines, and how bigger capability they are. Let's say predecessor, which was Skyway 100, have capability of was 100 ton shift shaft load. Was a double wrap. It means that real load was 50 ton. Now we have 70 ton. What comparing to double wrap is 156, almost 160 ton of real load on the shift shaft load. Now efficiency. I will show you a little more how this technology is done. We're achieving 97, 90.5, 96.5, and 96% of efficiency at rated speed. And you will see if you also what it means for current. Let's say a moment ago, I was looking for this 1600 what Johansson showed here, and what current was over there. And you can see here when the much bigger machine, which is this one, have a smaller current, it means that efficiency probably is higher, at least 4, 5, 6 points. And now the masses of this machine, this almost is 40% much lighter than predecessor, and can be transported up with parts. Next, this is why I mentioned about installation. We don't need to do this. This is from Burj Khalifa, Skyway 100 machine lifted up when we have to build special crane and platform and pick it up to be capable to pick it up and install. The same when we're talking about the access around the machine. With new code recommendation, this machine simply with machine room will interfere with walls. the new machine is access around is easy and can be installed, and even more symmetry around the central line allow us to locate machine directly on the elevator shaft in any direction we want. And if multiple machines in a machine room, it also can be arranged very easy. Now, a little closer view of this machine. This is Skyway 400, ready to install in our test tower. And here also you can see guts of this machine. This is without mechanical stand, but this is a test in our facility to find out performance and confirm performance, reliability, and currents and thermal and everything which is meeting our requirements. And how this machine is built, this is like I'm coming a little more to technical, to details. Maybe this conference is a little about high level of technology information, but I would like to bring a little closer to it. This machine is built as a external rotor. It means that whole stator is inside external sheath, and winding on a stationary part inside of this drum with sheath, and is supplied with through the cables going to the hollow shaft inside. And we also have a blower. It's only one blower, which is variable speed, and blower only works when it's needed, and with variable speed, which is adjusting needs for cooling air. We have 2 bearings only, and bearings are in special cartridges and lubricated with oil. And this cartridges has a special opening and windows when we can observe all the time level of oil and contamination of oil and replace it. And this kind of feature allow us for big saving in time of changing lubricant. Changing oil in this kind of machine is taking 1 hour. When somebody was dealing with grease, it's taking almost a day. And downtime of the elevator is 1 day. This machine has caliper brakes, series 200, 250, and 400 electromagnetic brakes, when 800 is hydraulic brakes, because it would be too many of them, and no electromagnetic can do its job. And also, for better traction, we have a proprietary grooving technology with special coating and a geometry of grooves to give additional proper traction. Let's go to next one. This is a little view which I would like to show how these machines are now constructed. And this is permanent magnet machine with embedded magnets in a rotor on the internal surface of the sheath. And this integration allows us use to also sheath material, which is cast iron, duct iron, which allow also to carry magnetic flux. In this way, the weight is smaller and dual function of sheath, not only containing ropes and giving traction, but also carrying magnets, magnetic flux, as well as partially removing heat from this internal space in a sheath drum. It's a stationary shaft with two cartridge bearings, and it's a stationary part with a stator with a concentric winding, copper winding, which each coil is installed on a separate teeth. And in this way, it's what we call torque motor or concentric winding motor, which is the highest performance from motor technology point of view. Winding is embedded in epoxy material, which we call for better mechanical, acoustic, and thermal properties. And air is pumped into the space, internal space of a machine, and is distributed from inside to stator along the back iron of stator, and is evacuated outside to opening in rotational drum of sheath. Also, you can see brakes here, and also this opening, this hollow stationary shaft allow us to do cables, providing cables supplying stator. All this, what allowed us to reduce the mass about 40%, it depends which machine, making much smaller size and making very, very efficient. Concentric winding have a very long, short end turns, then copper losses are much lower in a typical motor. This also small air gap due to not big distance. A small air gap also allow us to utilize electromagnetically much better and give us a much higher efficiency. Okay, let's go to next one. This is, I added this, listen to this battle about what kind of speed we should have. Everybody wants 18 meters, 20 meters per second. Maybe somebody will like to have a 22, why not? If somebody likes it. And I want to, this is example with our 400 machine. I calculated to show a little what makes sense or not. And data is here. I put like a machine with some kind of traffic pattern, 24 hours. I use start per hour. I use 55. Each run 80% duty load, 5,000 kilogram, 15 meters per second, rise 300. And acceleration 1 meter per second. But first, heat release, and I will go to the speed little for the next slide. On the left, you can see how efficiency of motor affecting losses. If I have a 96.5 motor efficiency of machine, I can have some, you can see per one run, 120 watts per hour energy used per double run, up and down. And drive is consuming about 140 watts per hour energy. When efficiency drop down by 1%, machine is constructed as a lower efficiency by 1 point, the usage of energy is increasing for motor much dramatically than for drive, supplying this machine for one cycle, and then for 2% is almost 3 times of what was for 96.5. It means that 2% in drop of efficiency is increasing almost twice of use of energy per one cycle. And this is recalculated for 1 day and running 336 cycles up and down. And we can see how much kilowatts per day we can save with 1% this efficiency. Then when machine is worse by 1% efficiency, and then when machine is worse by 2% efficiency. And this is real money. It means that it's a very sensitive how good components are, how good subsystems are. I understand the traffic, I understand green, I understand this organizing whole building, but this is where we're starting. We have to have a component which are very, very good and to use them. And now to this same data, but I set 1 meter per second square acceleration. This machine, if you did in this system, the 15 meter per second with 1 meter per second square will never reach a 15 meter per second speed. Will be only 13.1. Then when we're looking on them, what to do, what kind of speed we want, we have to look on everything. Then we have to use probably 1.25 meter per second to reach the speed of 15 meter per second per 1 second or 1.5 second. How worthy it is, but 1.25 meters per second, which is 25% higher acceleration, it means that my losses are much higher because I have a much higher dynamic torque. And then I'm showing here some kind of graph to what kind of losses we have, copper losses and so on when going up, and also all energy per one cycle. This is when elevator 80% loaded going down. It's input power, output power, and losses. Red is copper losses in a machine. But this is only to give you some example to consider when we're talking about the efficiency of machine, when we're talking about what kind of speed we need, for what kind of rise we need, because behind it we're paying if you're doing not the best job. When we're choosing, like for record, if you want to have a 20 meters per second, yeah, we're offering 20 meters per second. Machine Skyway, SkyMotion 400, yeah, we can offer, we can build, we can deliver to 20 meters per second for this machine. Now, this is current, and this is what I mentioned. This is with full, you can see current for the 5,000 kilograms and 15 meters per second total current, because it will be two drives. I will talk about a moment ago. We saw like a 13.4, 1.4 5 kiloamperes of current. When like 20 minutes ago this current was on this level when we're talking about 1,600 kilogram duty load and 12.5 meters per second. Probably the efficiency somewhere for this case, for this motor is better. And this is data now. How this machine is organized. You have a few winding system, each of them, and can be 250 SkyMotion and SkyMotion 400 is a real three-phase machine. When the biggest machine, SkyMotion 800, is real six-phase machine. And can be, if you have a two winding system, they have all machines have the same coil. If this would be SkyMotion machine for 12 meters per second, 8 meters per second, 15 meters per second, the same coil. It means that I have one design and I can do only by changing connection. And then can be work with two drives or one drive. The same machine, this machine can work with two drives or one drive. This machine can work with 2, 4, or 1 drive. Or if I want to only, so for instance, this machine can work, if I wanted to work only with one drive, big drive, or biggest drive, but I can take two smaller drives because they're more valid economically, and use twice smaller drives by two of them, and have a better economical solution. And the last slide, before conclusion, this is example of this, what I said. Can be 1, 2 drives, can be 4 drives, can be different number of drives. I don't have to develop any new drives. We're using the same, we design it, and this was requirements. We want to design to the drives what we have and proven technology for many, many years. And this is a flexibility with this. Coming to the conclusion, SkyMotion system presents significant extension to super high-rise elevator capability. 600 meters rise, 5,000 kilogram duty load, 15 meters per second, in some cases 20 meters per second. The reduced weight, decreasing the size of and cost of the hardware, logistic expenses, and time devoted to installation. And higher efficiency, as I tried to show, is giving us energy saving and decreasing ventilation requirements for machine room, and size also reducing footprint for machine that can be installed easy in any environment. Thank you.